All right, I got some problems put together explaining the uses of the trig identities and including angle and sum, double angle identities. How do we make use of these things? What kind of problems do you need to be able to do with them? So I got a short mix of things just to use as examples, but also point out the basic ideas of it. For verify problems, we know this is supposed to be true for all values of x, at least within the domain of these things, right? There's somewhere these would be undefined. But for other values of x, this should be equal to this all the time, and we just want to find out why. The basic work that you're doing on this, then it's kind of a proof of this idea that this is true. And we want to just pick a side of this thing to rewrite, mostly using algebra stuff, but also trig facts. Rewrite it until we can get it to look like the other side. So you kind of pick whichever side looks like it has something to do on it, right? This is kind of just sitting here, it doesn't leave you much, but this, we got some stuff to do over here, so I might start rewriting that. Putting everything in terms of sine and cosine is a good idea, because our basic identities involve those. So secant squared is 1 over cosine squared, and this turns into sine squared x over cosine squared x. So you could write that in terms of tangent, but if we're trying to get these things put together, I'm going to do what the algebra person would say to do with 1 plus a fraction, and that's get a common denominator. Right? Algebra instincts should say, oh, I need this over cosine squared x as a common denominator. So then you'd get cosine squared x over cosine squared x plus sine squared x over cosine squared x. It looks like that. And then trig person would recognize that's your Pythagorean identity. So that's equal to 1 over cosine squared x, which is, of course, just secant squared x. So that comes out to what it's supposed to. That's kind of what you're trying to do with verify the identity problem, is pick whichever side looks like there's some simplifying or something that can be done with it. Work on it. You can keep in mind where you're supposed to end up, but you kind of work on this just using the identities that you know, or the facts that come up in here, until you can make it look like the other side. And that can take a little bit more work than that sometimes, but there's some basic ideas. Putting things in terms of sine and cosine, and then using algebraic properties and basic algebra processes takes care of a lot of it. Some of these problems, they have an identity, but they don't tell you what the other side is supposed to be. So that's kind of the same thing. I'm going to do what trig and algebra would say to do on this side. I'm just going to try to simplify it down as much as possible. And there's more than one way to write this thing that's right here. We could get different answers as long as they're equivalent as functions. We could have this looking a little different. But the clear thing to do is, again, I got fraction minus fraction. So you do what algebra says to do, get a common denominator on this, which is going to have to be sine x cosine x, right? So just working on these in algebra class lately, I want to know how to get these written with that common denominator, and then I can do the subtraction. Right, this is over cosine, so I'm missing the sine. I got to do times sine x on the top and bottom of this fraction. So that ends up being sine x cosine x plus sine squared x. We get a lot of powers like that. Trig function squared happens a lot in this section. This one we're going to be multiplying top and bottom by cosine x to get this common denominator. That's the missing factor here. So that distributes to both of these, and I got sine x cosine x minus cosine squared x. So then algebra says now that you have a common denominator, you keep the common denominator and go ahead and do the subtraction on top. That's sine x cosine x minus sine x cosine x. Those are opposite terms. This is here, I got sine squared minus negative cosine squared x, which is a plus. And that should show up again. This Pythagorean identity shows up again. Sure enough, that's just 1 over sine x cosine x. So you could write that. You could write just that for the answer to this one, but you might also recognize you could break this up as 1 over both of those and write secant x cosecant x. You could leave it in 1 over form, or you could put it in those reciprocal functions. That's fine. Those That product is what this whole thing simplifies down to, and that's what you're trying to do with those. Angle, sum, and difference properties are useful in a few cases, being able to break these things down. This problem's kind of using it in an interesting way because they've got the broken up piece. That this is the result of this angle difference problem. See, if you have two angles or two inputs in here added or subtracted, there's formulas to break these things down. And the one that we're dealing with in this one says that the cosine of when we have subtraction there, alpha minus beta, that it's equal to, you can put it in terms of the individual functions this way, the cosines of the individual functions and the sines of the individual functions multiplied. That ends up being true for any angles there. If that's a minus, this is a plus. If that's a plus, you get a minus here. That's the angle sum property, but this one's a difference. So the plus is correct. This is already then in the form of the left side. So if we put it back over here, what we're doing is alpha is the 7 pi over 12, and beta in this is the 5 pi over 12. So if we go ahead and put it together into your angle difference thing, you get that this whole thing is equal to the cosine of alpha minus beta. 7 pi over 12 minus 5 pi over 12, which is 2 pi over 12 or pi over 6. So that is, well, it says to write the expression as the cosine of an angle, so I guess that's my answer right there. I know that comes out nice. It came out to a nice exact value, so that's actually just square root of 3 over 2. But they want that written as one thing there. So you can use this to take something like that and break it up in pieces. Or if things happen to have exactly those pieces, then you can put it together and get a single expression out of it. That's what that identity tells you. All right. Another one of these using the sine of alpha plus beta. That got broken up by the printing here, but it's the sine of alpha plus beta. That's another one of these angle sum properties to use. We're going to try to break it down into the values of the individual pieces. I want to know about alpha and beta separately so I can plug in what I know. So I'm going to use the identity here. The angle sum property for sine. For a plus keeps the plus, but it mixes the functions together. This is sine of alpha, cosine of beta, and cosine of alpha, sine of beta. That's the formula for the angle sum property for sine. That's how that breaks down. Now, we're given some of this information directly here, and we're given some of it kind of indirectly where I have to think this through. So we're actually given cosine of beta, and none of the rest is this stuff immediately, right? Cosine of beta is negative 5/13. I need to know the rest of these things. And they don't give me any of the rest of it, but they give me some weird information about tangent over here. But we're going to use, we know about trigonometry to break these things down. Unit circle way of thinking of it is kind of nice. Theta lies in quadrant 3. We're over here. The slope is 21 over 20. So there's going to be some point here, x comma y, where y over x is 21 over 20. But x squared plus y squared equals 1. So y can't be 21 and x can't be 20. That would be way too big. Right here, this has got to be 21 over some r. And this is 20 over some r, but r is 1. I'm sorry. X squared plus y squared is equal to 1. I'm using r there, but 21 over r squared plus 20 over r squared equals 1. That's got a common denominator already of r squared. And if you add that up on top, 21 squared plus 20 squared ends up 841. So r squared equals 841. R is 29. They have this thing set up so that that square root comes out pretty nice. But these are actually negative. We got to keep that in mind. That's the quadrant 3 part. These have to really both be negative. R is plus or minus the square root of 29. We actually need these to be negative. So this would be negative 21 over 29. And x would be negative 20 over 29. Those are the actual values on the unit circle there. And so that's sine and cosine of that thing. Sine of alpha is negative, well, it's the y value there, negative 20 over 29. Or did I turn that around somewhere? Y was 21. Okay, that's 21 over 29. And x is 20, so an x over r is negative 20 over 29. Sine beta I also don't know, but I know cosine of beta. And I know sine squared plus cosine squared equals 1. So I'm going to use another identity for that piece. I got to fit this in somewhere. But sine squared beta plus cosine beta squared equals 1. So sine squared beta equals 1 minus 25 over 169, and that comes out to 144 over 169. So sine of beta is plus or minus 12 over 13. Again, I have to know the quadrant. That's why they gave me this extra information. Alpha is in quadrant 3. Beta is in quadrant 2. Beta is the one I'm working on now. Beta is in quadrant 2. That means x is negative and y is positive. It means cosine's negative. Yeah. Sine is positive, so this is actually going to be positive 12/13 because of the quadrant we're in. So that's what goes here. And then it's just putting those together to get the value that we're looking for. Sine of alpha plus beta would have to be equal to this. You've already got a common denominator there of 29 times 13, which is, I think, 377. And this is 105 minus 240, so I got a negative 135 when you put those fractions together. That's the exact value of sine of alpha plus beta there. Quickly, this is the same thing, but in a much simpler situation. If tangent is 4/3, beta lies in quadrant 3. That means you got a slope of 4/3 down here in this third quadrant again. Y over x is 4/3. And we're trying to find the x and y. We go there. So 4 over r squared. Well, it's really negative 4 and negative 3, but it's going to be squared here anyway. So r squared equals, what you end up with here is 25 over r squared equals 1. R squared is 25, so r is 5, and this is really negative 4/5 is the y value. And negative 3/5 is the x value. And so that's cosine and that's sine of theta. We're supposed to find sine of 2 theta. This is a double angle formula that gets rid of the 2 and breaks it down to the individual pieces. The identity here, or formula, says that sine 2 theta is 2 times the sine of theta times the cosine of theta, which is a handy way to break it down into individual pieces. So the value of it here would be 2 times sine theta cosine theta. Comes out 2 times 12, positive 24 over 25. Sine of 2 theta there. Now an angle that's here is between 180 and 270 if you were going in degrees. If I doubled that angle, that gets me somewhere between 360 and like 540. So the sine is going to be positive on this. It's going to end up here. So that looks right with that. And number 6 here. rewrite the expression as an equivalent expression that does not contain powers of trigonometric functions greater than 1. If you don't like having exponents around, and believe me, when we're doing calculus on these things, we don't like having exponents around. But also, you don't probably know just from looking at it what the graph of that looks like, because it's squared instead of just being a regular wave function, right? Well, turns out it is a regular wave function. We got to put it in terms of stuff that doesn't have the squared in it. And these are related to this identities for cosine squared. I want to talk about where this comes from a little bit. But cosine of 2x, this is your double angle for sine, was nice and simple. Your double angle for cosine really isn't. It looks like cosine squared x minus sine squared x, which is a little weird looking. But you can write this a couple of different ways. If you put in everything in terms of cosine instead, you get 2 cosine squared x minus 1 equals cosine 2x. Or another way of writing that is 1 minus sine squared x minus sine squared x. If I replace the cosines and put everything in terms of sine, it looks like this, 1 minus 2 sine squared x. And you see what happens if you solve for cosine in either of these, or actually solve for cosine squared. We're going to add 1 and divide by 2, so you get cosine squared x equals 1 plus cosine of 2x divided by 2. And if you do the same thing down here, subtract 1 and divide by negative 2, it ends up looking like, well, I'm going to turn that around. It ends up looking like 1 minus cosine of 2x over 2. Those end up pretty similar, but they don't have the exponent in them. So it's a way to write squareds in terms of just a double angle thing, which is nicer for some stuff. So this expression ends up equal to 8 times this whole thing. 8 over 2 is just 4, so I got 4 plus 4 cosine of 2x. And so it is just a wave function. You could actually graph this because you just have a midline of 4 and an amplitude of 4 and a period of pi, right? You could use your regular graphing stuff to graph this. It's going to oscillate between 0 and 8, which is what that does. It's always positive. But this form, you know all about the graph of it. This form is also easier to do a lot of things with because you don't have a squared in there. It's a cosine function, just with a multiple. So this one's nicer to deal with in calculus for sure. So writing things in that form helps you out a lot with some stuff you're going to do in calculus with sine squared and cosine squared. So a good example of that. And it's kind of some quick examples that I hope help you as you're going through the chapter 7 material here.